Circles are something different from all the objects that we've talked about up till now. So far, everything we've seen has been made up of straight objects or pieces of straight objects. A circle, on the other hand, is defined to be the set of all points that are a constant distance from a fixed point. When you pick a point called the center and a distance called the radius, and you try drawing all the points that meet this definition, you end up with the curved shape that we usually think of as a circle. The words radius and diameter are both a little different from the definitions we've seen so far because they can have two different meanings. They can each refer to a segment within a circle, one from the center to the edge for the radius, and one from edge to edge going through the center for a diameter, as well as the lengths of those segments. Now, thinking about those distances, notice that since the radius is halfway across the circle and the diameter is all the way across, the diameter is always going to be twice the radius. One of the key properties of a circle is what we call the circumference. This is actually an idea we've kind of talked about before. Circumference is the distance around a circle. Now, you remember when we're talking about polygons, we talked about something similar, but just had a different name. It was called the perimeter. Now, the circumference of a circle is actually kind of special because if you draw a circle, any circle, doesn't matter how large it is, you take the circumference and divide it by the diameter, it always equals the same number. And that number's got a special name. We call it pi, and that's what this Greek letter here represents. Now, once we've got this relationship, we can also simplify this a little bit. We can get rid of the fraction, solve this for the circumference, right? And if we do that, we get this equation here. The circumference is equal to pi times the diameter. And remember, the diameter is twice the radius. So we could also rewrite this again as the circumference is equal to 2 pi r. Now, numerically, pi is a little difficult to pin down. Right? Pi is what's called an irrational number, which means that if we try to write out the decimal version of it, it never ends and it never repeats. Right? So if you're doing some calculation and you need to have an actual number for your answer instead of something with that little Greek letter in it, then you're going to have to use an approximation. Right? Usually when we want a decimal value, we'll use 3.14. And if you need a fraction, we'll use 22/7. Those are both really close to the actual value. So got a nice formula for the circumference, right? If we know the radius, if we know the diameter, all we have to do is multiply it by pi, and you've got the distance around. Okay, so how about the area? Well, finding a formula for the area of the circle and doing this exactly requires a little calculus, and that's beyond what we're going to be talking about here today. What we can do is we can use an approximation technique that was known to Chinese mathematicians over 1,000 years ago, and that actually kind of closely mimics the things we would do if we were doing this using calculus. Right, so what I'm going to do is I'm going to start with this circle here, and I'm going to assume that the radius of the circle is r. And I'm going to take the circle, and I'm going to cut it into 4 equal pieces, 4 quarter circles. Then I'm going to take those circles, and I'm going to line them up side by side with those kind of corner points, for lack of a better word, all touching and on a line. Now I'm going to duplicate those 4 pieces up on the top. I'm going to close it up here at the end. And now I'm going to draw one more line. I'm going to draw a line through the upper corner points, parallel to the line I drew through those so-called corner points down at the bottom. Now, if you look at this shape here, the shape made by those 2 parallel dashed lines, and this line here, you get a parallelogram. We have a formula for the area of a parallelogram. Now, that area, it's not going to be super close, right? It's not counting these pieces down here. And obviously, you've got the additional white pieces up in there, but those are identical to the blue ones. So in theory, I could just take the parallelogram's area and cut it in half and get the area of our circle. But there is the question of that overage. So how about if we just refine our dissection of the circle? Right? How about if we take the circle and instead of cutting it into 4 pieces, we cut it into 10 pieces? Right? We increase the number of sections. If we do that, The diagram looks like this. Now the overage, right, this area down here that isn't being counted is much, much smaller. So if I look at this and say, okay, well, let's just kind of politely ignore that, all right, and figure out what the area of our parallelogram would be, right? It will go something like this. The height of the parallelogram is this distance here, but that's really close to being the radius of the circle, right? So remember, the area of a parallelogram is the base times the height. The height is r, and the base is this distance down here. But that's made up of all the exterior sections of the circle. So that distance is going to be, again, approximately equal to the circumference of the circle, which is 2 pi r. If you multiply this out, you get 2 pi r squared. And remember, we're actually have twice as many sections here as we need because we don't want to include all of the white pieces up here. We just want the blue ones. So if we take my approximation for the area of the parallelogram and cut it in half, all that's left is going to be the area of the blue pieces that made up our circle, and that's pi r squared. And that is the formula for the area of a circle. So in the next lecture, we're going to look at two kind of classic problems and see how we can use these formulas to actually do some calculations.